Hello and welcome to our introductory series on basic GIS using QGIS. My name is Anurag Verma and I am a GIS expert with over 15 years of experience. So this series is brought to you by the Beyond the Campus. If you are looking to dive deeper into the world of GIS, consider enrolling in our comprehensive full stack GIS bootcamp. This bootcamp covers over 17 tools, software, and modules, includes 22 plus real-world projects, offers 5 industry-recognized certificates, and provides 100% job placement, assistance, and referrals. For more information, check out the link in the description below. In this series, we are focusing on the basics. It is designed for beginners, so even if you are new to GIS, you are in the right place. By the end, you will have a solid understanding of what GIS is, how to work with spatial data, and how to perform various analysis using QGIS, one of the most popular and accessible GIS tools available today. Why do we need GIS? Well, GIS or Geographic Information System is a powerful tool for solving real-world problems that requires an understanding of location and spatial relationships. Let's look at some examples to see how GIS helps in our day-to-day lives and the complex planning. Imagine you need to locate the nearest taxi cab stand from where you are. You want to find a nearby restaurant. You are looking for a property to buy in a specific area. You need to know the location of a sewer pipe to connect it to your house's outlet. Or perhaps you are involved in designing a road alignment for a proposed border road. In each of these cases, GIS can provide the spatial insights needed to make decisions. For instance, GIS can quickly find the nearest cab stand based on your current location or suggest directions for reaching a desired location. GIS is not only helpful in our daily lives, but it is also essential for larger, more complex issues. For instance, in urban planning, GIS plays a key role in determining where to build new infrastructure like roads or bridges, ensuring they are in optimal location. Environmental scientists use GIS to assess the impact of natural events like floods or earthquakes. After an earthquake, for example, GIS can help in estimating the extent of damage and identifying the areas most affected. GIS also plays a crucial role in disaster preparedness. By analyzing data, it can help predict where an impending cyclone might make landfall or how much land will be flooded if a dam were to fail. GIS allows us to ask and answer complex questions like where is the best place with the optimal mobile network coverage? How should we design a bridge considering the flow pattern of the river? In summary, GIS is essential for solving spatial problems across diverse fields, from public safety and disaster management to environmental conservation and the urban planning. It helps us make informed decisions by providing a spatial perspective to our questions. Now, let's take a brief look at the history of GIS. This is the picture of Dr. Roger Tomlinson, who is often referred to as the father of GIS. GIS as a field traces its origins back to 1960s when Dr. Roger Tomlinson, a Canadian geographer and a computer scientist, developed the first GIS system. At the time, he was too working with the Ottawa Municipal Corporation and was assigning the task of managing various types of network data such as gas pipelines, telephone lines, power lines, roads, and sewer networks. The challenge was that each of these networks had its own set of assets, and, whenever repairs of or new constructions was planned, there was a risk of damaging assets from other networks. For example, digging to repair a water pipe could accidentally damage a nearby gas line or a power cable simply because the exact location and the relationships of these networks were not effectively managed. Dr. Tomlinson's goal was to create a unified system that would integrate all of these network assets, allowing each department to see the relative locations of the different networks. This would enable workers in one department to understand the location of assets in other networks, helping to avoid costly and dangerous damages. To address this issue, he developed a system that allowed the visualization and analysis of spatial data in an integrated way. The system became known as the Geographic Information System or GIS. Dr. Tomlinson's pioneering work laid the foundation for the GIS field, which has since grown into the essential tool for managing, analyzing, and visualizing spatial data across various industries and sectors. So now we will look into the GIS process diagram. This will help us understand the infrastructure behind Geographic Information System and how various GIS products are gathered and processed. Let's break it down step by step. Everything begins with the sun. Sunlight reaches the earth and is either absorbed or reflected by the objects on the surface. This reflected light is captured by our eyes, allowing us to see different objects as our brain processes the information. The same basic principles applies to cameras and the other sensors. They capture light to create an image. Now imagine this process on a larger scale. When cameras or sensors are mounted on devices like drones, aeroplanes, or satellites, they can capture images from above, creating aerial or satellite images. This is the foundation of remote sensing. These sensors capture images of the Earth's surface, providing valuable data from a bird's eye view. After capturing the images, the next step is transmitting this data to Earth. Satellite sends the raw imagery data to receiving stations on the ground, equipped with satellite data receivers. These receiving stations act as a bridge between space-based sensors and our systems on the Earth, collecting large amount of raw data that we can process and analyze. Now we have this raw data, it needs to be refined. Raw satellites data is often unstructured and may contain noise or unnecessary information. So we use specialized softwares and data processing techniques to clean and structure this data, creating what we call raster data. Raster data is essentially a grid of pixels, where each pixel represents a small area of the Earth's surface with specific information like temperature, land cover, or elevation. Like in this picture, we are showing the land cover. This process raster image is structured and ready for analysis. While raster data gives a detailed view, it's often useful to have a different data format for certain types of analysis, especially for features like roads, buildings, or land boundaries, as you can see over here. That's where digitization comes in. In digitization, we trace features on the raster images to convert them into vector data. Vector data represents features in the form of points, lines, and polygon data. Points can represent specific locations like wells or buildings, as we are showing buildings here in this point data format. Lines represents linear features like roads or rivers, whereas polygon represents larger areas like fields or lakes. As you can see, we are showing this park as a polygon data. So to summarize, the GIS process involves capturing images through remote sensing, transmitting them to Earth, processing the data to generate raster images, and then converting it into vector data through digitization. This vector data can then be used in GIS applications for various analysis and to make informed decisions in fields such as urban planning, agriculture, environmental management, and disaster response. Now that we understand what GIS is and its origins, let's explore its relevance in today's world and why it is so essential across various industries. Today, GIS has become an invaluable tool in countless sectors, providing powerful decision-making capabilities that support businesses, government, and communities in managing spatial data effectively. Here is a closer look at some ways GIS is currently applied. Like in various industrial applications, powerful decision-making tools for any business or industry, analysis of environmental, demographic, and the topographic data. It also acts as a decision support system. It helps in the environmental impact analysis, disaster management, and the natural resource management. GIS also helps in project evaluation and monitoring. It also gives a view of planning and simulation modeling and the prediction of the future possibilities. So in that way, GIS is helping many industries and government organizations so that they can plan better and make new kind of possibilities for the new generation. GIS is widely used across multiple industries due to its ability to map, analyze, and visualize spatial data. Let's take a closer look at some of the specific applications, such as mapping, telecom and network services, accident and hotspot analysis, urban planning, transportation planning, environmental impact analysis, agriculture applications, disaster management and mitigation, navigation, and banking. GIS also serves in taxation, surveying, geology kind of applications. Assessed management and maintenance plus damage estimation is also possible with the help of GIS. GIS is widely being used in the dairy industry, planning and the community development, natural resource management, irrigation, water management, and pest control and management. So in that way, GIS is being used in the various industries and various organizations, as you can see in this slide. Let's now discuss the definition of the geographic information system in a scientific manner. There could be many definitions of the geographic information system, but I am referring here the Premier Institute ITC the Netherlands, according to which a geographical information system GIS is a computer-based system that provides the following four sets of capabilities to handle geo-reference data. First is data capture and preparation. Second, data management, including storage and maintenance, data manipulation and analysis. And fourth is data presentation. Here in this diagram, you can understand it more clearly that first by the GIS we can do the data capture and preparation. After that, storage and maintenance. As well, we can do the manipulation and analysis, and by doing all this, we can do the data presentation in the GIS or the Geographic Information System. So under the definition, we will discuss the data capture and preparation first. Data capture is the process of collecting raw spatial information. This can include surveying, which is using equipments to gather precise geographical data. Second is photogrammetry. It is extracting information from the photographs, often used in mapping. Third is remote sensing, which is collecting data from satellites or aerial imagery to capture large areas, whereas fourth is digitization, which is converting the analog maps into digital formats that can be used in GIS. Digitization can then further be divided into three parts, which is manual digitization, semi-automatic digitization, and automatic digitization. Manual digitization is done with using line entry through keyboard, digitization table with the cursor, computer monitor and mouse, and use of photogrammetry. In the semi-automatic digitization, we use line following software, which is called trace software. Third is the automatic digitization, which is a scanner followed by the digital conversion. So all these are the different methods and devices for the digitization. The available digital data inputs for the data capture and preparations are CD, DVD, USB, drives, internet, and the web services. Now the data organization, storage, and maintenance step of the definition says that the data organization in the GIS should be based on the principle of representing the real world phenomena. Here you can see that we are having three kinds of data, which is one is the street data, one is building data, and one is vegetation data. And these different data are stored in three different layers, data layers. One is this is street data layer, this is the building data layer, and this is the vegetation data layer. And when we integrate all these layers together, we find a real world phenomena. So spatial data is organized in different layers based on their theme or scale. And the different thematic categories which can be used in GIS are land use, topography, administrative areas, etc. GIS data can be organized into two main types, raster and vector. Each type has unique characteristics and storage methods, making them suitable for different types of spatial analysis. Raster data. Raster data represents the world as a grid of cells, each holding a value that represents information like elevation, temperature, or land cover. Think of it as a digital image made of pixels. In a raster file, data is stored as a long list of values, one for each cell, preceded by some extra data that specifies properties like the grid's dimensions and the location of each cell. This encoding scheme is known as row ordering, where data is stored row by row across the grid from top to bottom. Vector data. Unlike raster data, vector data represent the world using vertices and paths, forming precise shapes. These shapes are usually categorized as points, lines, and polygons. Point represents specific locations like a city or a well. Line shows linear features such as roads or rivers. Polygon defines areas like country boundaries, lakes, or land use zones. Vector data can be stored in various formats, either as files such as shapefiles, GeoJSON, or within the spatial database. This format especially represents discrete features and allows the precise measurements and spatial analysis. Understanding these differences is crucial as raster and vector data are used in different types of GIS applications. Raster is ideal for continuous data like elevation or temperature, while vector is better suited for discrete features like road, boundaries, and buildings. In GIS, effective storage and maintenance of data are essential for ensuring data accuracy and usability over time. So in storage, GIS software packages support two primary types of data: spatial data and attribute data. Spatial data is stored using a vector approach. This allows GIS to represent locations and shapes such as points, lines, and polygons in an efficient and a precise manner. Whereas attribute data, which describes the characteristics or the qualities of the spatial data like population, land use type, or elevation, is stored in tables. These tables are linked to the spatial data, allowing users to query and analyze both location and attribute information together. Now coming to the maintenance. Data maintenance is crucial to keep GIS data reliable and relevant. It involves combination of activities aimed at keeping the data set up to date, ensuring it remains accurate and beneficial for user communities. This process includes obtaining new data when available and replacing the outdated data to reflect current conditions. Proper maintenance not only supports existing users but also makes the GIS systems more versatile and dependable for future applications. In summary, efficient storage and regular maintenance are essentials to ensure GIS data continues to serve as a valuable tool for the decision making and analysis. Now moving forward to the third step of the definition, which is data manipulation and analysis. One of the most distinguished aspects of GIS is its powerful capability of spatial analysis. GIS spatial analysis allows us to derive new geographical information that wasn't directly available in the raw data. This is where GIS truly shines, helping us uncover patterns, relationships, and insights from spatial data. Using analysis function, GIS integrates both spatial and attribute data, which helps answer complex questions which are posed by the users. For instance, GIS can help us find suitable land for new development. It can analyze flood risk zones or assess agricultural productivity. These GIS functions are not only essential for analyzing spatial data, but also for maintaining it. Regular analysis and updates keep the data relevant and accurate, supporting informed decision making. GIS plays a critical role in spatial decision making and serves as a spatial decision support system, which is SDSS. This means GIS not only provides information but actively assists in making strategic decisions based on geographic data. So GIS ability to manipulate and analyze spatial data is what makes it an invaluable tool for a wide range of industries and applications. Now coming to the fourth and last part of the definition, which is data presentation. So another useful aspect of GIS is its capability to present spatial data and analysis result in a user-friendly manner. GIS data presentation makes complex geographic information more accessible, helping users understand spatial patterns and insights. To achieve this, GIS uses various methods and devices tailored to different formats and users' needs. These are the different methods and devices. For hard copies, GIS data can be printed using printers for basic output. Plotters like pen plotters, inkjet printers, thermal printers, and the electrostatic plotters for detailed maps. And even film writers for the high quality imagery. For soft copies, data can be viewed directly on a computer screen, making it easy to interact with maps and layers digitally. In addition, GIS data can be distributed as a digital datasets using magnetic tapes, CD, DVDs, USB drivers, and through the internet also. Lastly, web services like GIS portals provide users with online access to GIS data and analysis, enabling real-time data sharing and interactions from anywhere. So GIS data presentation options allow users to view, share, and interpret spatial data in both physical and digital formats, making it a versatile tool for communication and decision making. After discussing the definition in detail, I would like to discuss this spatial data layer concept in detail, which is very important in GIS. A spatial data layer is essentially a representation of a specific spatial field. In GIS, spatial data layers can be continuous, like raster data, or discrete, like vector data, or they may represent a collection of similar objects, as you can see over here in this diagram, where I have shown you different types of spatial data layers. In a spatial database, data is organized so that a similar type of objects are grouped into a single layer. This makes the data easier to manage and analyze. As you can see, all the elevation data is in one layer, whereas transportation, addresses, boundaries, water features, and survey control points all are in different layers, which are referred to as different kind of spatial data layers, and all these layers together are representing the real world in a whole. For example, all point data such as electric poles would be stored in a single point layer, and all the line data like railway tracks would be stored in a line layer. As you can see, I have stored all the kind of water features here in the water feature layer. This approach ensures that each spatial data layer is focused on a specific type of object or a field, making spatial analysis more efficient and organized.